This thing does not move. Yeah. So first things first, why do we even care about algorithmic fairness? So as more and more of these machine learning systems are being used in applications that are socially very, very important, like criminal risk assessment, mental health monitoring, so on and so forth, people quickly realize that it's not enough that our algorithms are only accurate. They need to be privacy preserving, they need to be robust, they need to be explainable, and they need to be fair as well. So in light of that, there are many notions of fairness that was developed in the context of supervised learning problems like regression and classification, so on and so forth. This paper, this Newrick's paper back in 2017, for the first time came up with a notion of fairness in the context of clustering algorithms. And their notion of fairness was based on something called disparate impact doctrine. It's a heavy name for a simple thing. So they basically define protected attributes. These protected attributes are attributes protected by a specific institute or the law of the state. This could be gender, race, this could be your marital status. It really depends on the particular application in hand. And they say your decisions cannot be, your decisions cannot disproportionately discriminate against people belonging to a specific class of the protected attribute. So you cannot discriminate against, say, biologically female individuals when your protected attribute of interest is gender, right? One silly example to bring this point home. So suppose I am clustering a bunch of individuals belonging to same demographics based on their heights. And I want to cluster them into two clusters. Now, invariably, in the cluster with higher mean height would have more males than females. In the cluster with lower mean height would have more females than males. Now look at the example. I do not take into account the gender of the individuals explicitly into account when I'm clustering them. I'm clustering them with, based on their height. But since height and gender are related, I end up discriminating with respect to the protected attribute gender. So it's not enough just to ignore the protected attribute and go about your business. You might be in trouble. Right? So what is the definition of fairness in the context of clustering? It's called balance. Suppose you have data which are denoted as xi, ai, and I runs from 1 to n. These xi's are divariate features, and AIs are the labels of the protected attribute. So you see data like height, weight, and say male, height, weight, and female, stuff like that, right? Now, there, the Chinseti et al. Definition of fairness in clustering is very simple. They essentially say you see a sample where and you look at the protected attribute, you look at the proportion of individuals belonging to the protected attribute in that particular sample. So suppose I'm looking at gender, males and females in the entire sample is in the ratio of 1:1. My clustering should be such that in each of the clusters, that ratio should be maintained. So in each of the resulting clusters, I should have males is to female equal to 1:1. So that ratio has to match, right? So if that ratio matches, we say the cluster is balanced, and if that ratio is off by a bit, it would be unbalanced, right? So how do they go about this? They would divide, so they would divide the entire sample into something called fairlets, which are minimal sets that are fair. Then they would just cluster those minimal sets using their favorite clustering algorithm. I'll try to use a picture to bring home the point. So suppose colors denote denote the label of the protected attribute. Suppose you have 4 individuals with the protected attribute blue, right? Let me draw it like this. And you have 4 individuals with the protected attribute green. Now, if you use this k-means and do a clustering, you'd get a cluster, probably get a cluster like this and this, right? Do we have balance? We do not, right? All greens and all blues. So we cannot do that. We would make minimal sets that are fair, then cluster those minimal sets. How to go about that? I would just do this, 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 and this. So each of these egg-like shapes define fairlets, and they are fair. In each of those smaller sets, the ratio of males and females is 1:1. Now, if we can define some sort of measure of center of each of these fairlets, I can just use k-means or something like that to cluster the centers, and the resulting clusters would be fair. Any questions with that? Because I revolve around this issue quite a bit. Any questions about how this is done?
Are you going to go into how these fairlets are chosen?
Yeah, so I'd be talking about that in a while. Yeah.
They might have like totally different characteristics. Just to make them fair, you're kind of clustering two very much different.
Right. So your need for fairness would be against your clustering objectives. But the task is so that you have to cluster the observations so that you maintain these fairness constraints. So this is probably true for any of the trustworthy ML sort of needs like privacy and fairness and so on and so forth. That would be against the clustering objective, but that is the constraint that you have to work within. Right? So this is how this is done, and they do it by bipartite graph matching. I'm not going into details, but once Chakraborty et al. Had this notion of balance in the context of clustering, like any other fields, there was a gold rush. There was a bunch of papers, right? Multicolor case means what happens if we have multiple protected attributes or protected attributes with more than 2 colors. How to study fairness in other forms of clustering, like spectral clustering, correlation clustering, and so on and so forth. How to study sort of fairness in clustering in conjunction with other notions that are required in modern times, like privacy and robustness. So we have so many papers. Why do we need to write 2 more, right? So here is my attempt to answer that question. In this paper, we take a model-based approach to solve this problem of clustering under balance constraints. If I go model-based, what are the advantages? I think most of you would be familiar with that. We'd get uncertainty quantification. We would be able to accommodate non-Gaussian data easily, and so on and so forth, right? But more importantly, from a theoretical point of view, could define a true fair clustering configuration in the population level. And you could come up with results on clustering consistency. While this requirement looks extremely theoretical, but once you have these results, you could come up with measures of performance evaluation. I could say this algorithm is better than this one. So that's why those results are sort of required. Of course, we are not the first ones to try to develop model-based methods for existing statistical methods. These are very well-known examples. People have created probabilistic PCA and Gaussian mixture models for clustering and so on and so forth for existing sort of optimization-based tasks. Right. So first things first. So far, if I go about the Chakraborty et al. Route, their definition of balance was extremely based on sample quantities, right? You look at the sample, look at the ratio, and so on and so forth. So how do we define the notion of balance in the population level? Zeta defines the ratio of points. Zeta defines the ratio of individuals belonging to different classes of the protected attribute. Suppose you have protected attribute A that has 3 levels, A1, A2, A3. Zeta tells you what is the ratio these 3 classes appear in the entire population. Now, our generative model is like that. We draw a multinomial that gives me a level of the protected attribute. And once we have gotten the level of the protected attribute, we would go about the usual clustering route, which draw a clustering index, and once we have the clustering index, we draw the component specific observations following some law, right? So this is the population level generative model. But remember, in data, we would only see the observations and the levels of the protected. We would not obviously see the clustering indicators. Those are sort of latent variables, right? So our objective is to learn about the marginal distribution of the marginal distribution of the clustering indices modulo balance constraints, or some notion of fairness, right? Now, if we look at here in this equation, what I do, I draw a level of the protected attribute, then I draw a clustering index, then I draw the observation. There is no notion of fairness yet in this generative model, right? How to sort of have that in the population level? We would only look at probability distributions where that criteria holds. What does it say? The probability distribution of A given Z matches the probability distribution of A. The probability distribution of A is basically a proportion of the individuals belonging to various levels of the protected attribute in the population. And when you condition on Z, you are looking at the same proportion, but constrained on a specific cluster, right? So Z is a clustering level. So when Z is equal to 1, you go into that cluster and see the proportion. When Z is equal to 2, you go into the cluster and see the proportion. Those proportions should match across all the clusters. And that proportion obviously match with the population level proportion, right? Now, that's a strict constraint. If you sort of need to develop MCMC algorithms, that could be very challenging when you have a strict constraint on the parametric space, on the parametric space. So we define a sort of relaxed notion of balance. So this is based on scale divergence between the contingency table of A, Z and the independence table of PA, PZ. So basically, if you look at the picture, it would be something like that, right? You would have males and females, and you have cluster 1, cluster 2. Now you would have certain proportions here. This is a contingency table, right? If it was independence table, these things could have been just, you could have gotten them by multiplying these two numbers. Right? If this was the case, we'd have we would have perfect balance. But now we are looking at situations where we might not have absolute balance, but we would allow some amount of departure. And the departure is sort of indexed by epsilon, and we would say A and Z satisfied epsilon balance under P X, Z, A if this condition holds. So we would let the table to be something close to this, but not exactly this, right? And that would be that would be determined by epsilon. Now, in the true generative model of clustering, there might not be any fairness constraint. So the true generative model of clustering might not belong to a class where this constraint is satisfied, right? So what we are going to do, we are going to look at this problem as roughly speaking, the MLE in specified setup, where the true generative model is not within the class of models we consider to model the data, but we would look at the best scale projection. And that is how we develop our theory, but we will not get into the theoretical details in this talk. I'd rather talk about a model that tries to achieve this task. So few notations. So we develop a model which looks like a hierarchical Dirichlet process. And in hierarchical Dirichlet process, there will be a parameter which fixes the highest number of clusters that we can consider. So that number is given by K, and G and B are lowest level prior hyperparameters in the model. But yeah, few more notations. Please bear with me in the slide. The model comes soon, right? So the big Z n comma K is the collection of all possible clusterings such that we have K clusters, right? And M is called clustering of occupancy vector. It essentially says, suppose you have 100 observations, what number of observations you have in each of the clusters. So this is called cluster occupancy vectors. And Zn, comma K, comma M is all possible clusters such that your entire data set is divided into K clusters and the cluster occupancy vector is M. So this can be written as a binary matrix. So suppose I have 4 clusters and the cluster occupancy vector is like this. I write down the clusters like this. And the cluster occupancy along these lines. So, so individuals, suppose I have the number of observations is n. This matrix will say, look at the first observation. In which cluster does it land in? Suppose it lands in the second cluster. And we do it for all the observations. Here, I'd have the cluster occupancy vector. And here, I'd have just one, because each of the observations would be in exactly one of the clusters. So this set can be uniquely written as collection of all possible binary matrices such that you have fixed row and fixed column sums. Is it clear? Any questions? This observation is required for our sampling, so that's why I'm pausing. It's just you have 100 observations, 1, 2, 3, 4, 5, 6, 7, 8, up to 100. You look at which cluster each of those observations fall in, and if the observation falls in the first cluster, you put a 1 here. If not, you put the 1 somewhere else, right? So here is a model that tries to, yeah.
For the weakest matrix, like we have 52 observations.
Yeah, we suppose we are clustering 52 observations.
Yes.
10 of them fall into first cluster.
Yes.
12 of them fall into second cluster. 14 of them fall into third cluster. 16 of them fall into fourth cluster. Now this matrix just records in which cluster each of those observations fall into.
Yes.
Right? So this is a row corresponding to the first cluster. If you sum up the numbers along this row, you'd get the cluster occupancy in the first cluster. Right? This is the matrix. I repeat, a binary matrix with fixed row sums and column sums. This is something that we need.
The second observation is in the first one. Actually, you are saying like the 1, 0, 0, 0, right?
Right.
Yes. You want to write it that way.
Yeah. Something like that. This could be 1 as well.
Yes. Yes,
Right.
And then the rest should be 0.
Rest might not be 0. 10 of them are 1. Let's just 0. The
Yeah.
column,
Yeah.
the column, if this one is 0, 1, all of these
Yeah.
will be 0. Right. So here's a model that tries to do whatever I discussed in a soft manner. The first part of the model looks like a hierarchical Dirichlet process, where I draw the concentration parameter alpha naught from a gamma distribution. Once I've drawn the concentration parameter alpha naught, I draw a global vector of proportions beta given that Dirichlet distribution, where G comes from the same G, and K is the highest number of clusters that we consider in the hierarchical Dirichlet process. Now, once you have drawn the global parameter beta, we would draw the clusters. We draw the attribute-specific weight vectors W1, W2, W3, the number of levels according to the number of levels that we have in the protected attribute. So these vectors are necessary, like right? WA and W1 and W2. So this is in what proportion the observations that have protected attribute A equal to 1 are divided into various clusters. This is this is a vector of proportions that says in which proportion the observations belonging to the protected attribute class A equal to 2 are divided into the clusters. So this would be something like say something like 1/3, 1/3, 1/3. If it is 1/3, 1/3, 1/3, we'd have perfectly balanced clusters. If the ratios are off, if it is something like 1/4, 1/4 and half, then we'll not have balance. So these weight vectors essentially determine whether our output would be balanced or not. And how do we sort of control that? We control that via the concentration parameter alpha naught, which again depends on G and B. So essentially, changing G and B, we could hit a target balance value. Our balance doesn't need to be 1. Going back to your question, if the balance needs to be 1, we lose out a lot on the clustering objectives. If we keep the balance a bit down from 1, we might not lose as much in the clustering objective. So you could formalize the interplay between your fidelity towards the clustering objective and your fidelity to the balance constraint purely playing with your G and B and playing with your concentration parameter alpha naught, right? So that's the additional flexibility you get when you have model-based approaches. So this is something that sort of formalizes what sort of balance we get for varying values of B and G. This essentially gives you a visual recipe for determining your prior hyperparameters B and G so that you reach a particular goal with respect to balance. So you could have a goal like, so this is from, suppose this is balance 1, you could, changing B and G, you could say that a priori, the distribution of balance should be like this. It cannot be, yeah. So a priori, the distribution of balance should be like this. So you can just play around with G and B and have the flexibility around that. Now, once you have drawn the weight vectors, in the big in A is the total number of observations you have that belong to a particular level of the protected attribute. So in male is the total number of males that you have in the entire sample. In female is the total number of females that you have in the entire sample. You take a round operator. Basically, you get the cluster occupancy vectors from these weight vectors by multiplying it by n superscript A and take some sort of a round operator. How do you go about this? Suppose your N1 is 100 and your W1 is 1/3, 1/3, 1/3. So you multiply it, you'd get 33.33 all the time. You'd get 33, 33, 33. But these three numbers do not quite add up to 100. So there is some minor adjustments. Maybe you would make one of these to be 34. So this is basically a box operator, a bit more flexible. Here. So if we are familiar with hierarchical Dirichlet process, this is the step where we sort of differ from hierarchical Dirichlet process. In hierarchical Dirichlet process, here they would have indicator vectors and they would draw indicators, and once they have drawn the clustering indicators, they would draw the cluster specific observations, the Xi's. But here we skip that step and we go about this step like this, and we name it as a lifted Dirichlet process prior. This is required to have strict control on the balance. In fact, if we have a lot of samples, our model would behave very similar to hierarchical Dirichlet process. If we have small samples, this model we have would give us more control over balance than hierarchical Dirichlet process. So this is the key difference of our model from Dirichlet process. So this is if I recap, this is how the problem our model looks like. The first bullet is exactly like the Dirichlet process prior, where I draw the concentration parameter global vector and the cluster occupancy vectors. In the second step, given the cluster occupancy vectors, my job would be to sample from the uniform distribution of all possible matrices such that the rows are like that cluster occupancy vector and the column sums are all one. So this becomes a uniform sampling problem. And this is somewhat different from hierarchical Dirichlet process. This step is really poses with a combinatorial problem, and this will pose a problem in the sampling step as we go forward. Any question with the model? This step is exactly same as hierarchical Dirichlet process. Then we have the lifted bit of it, which is different from hierarchical Dirichlet process. That's why the drawing of indicators is different from hierarchical Dirichlet process. And once you have drawn the indicators, you can stick in your model of choice. It could be normal, inverse, gamma, anything whatever you like. So there is no play over here. Once you have had the clustering prior, the cluster specific likelihoods could be anything of your choice depending on the application that you have. Sampling, yeah.
Drawing the clustering indicator is difficult because you have to respect the ifs, right?
Right. So you have to basically draw one of these binary matrices, and that cannot be any binary matrix. That has to have fixed row sum and column sum. So this is a combinatorial problem, right?
Thank you.
Sampling beta and alpha naught. It's not available in closed form, but not super difficult. Snigdha, Dr. Pati, and some others had a paper. We could use that, or you could use something else to sample from beta and alpha naught. If you sample the weight vectors, those are Dirichlet, no problem with that. But as I mentioned, this is the difficult bit. We use a clever trick based on discrete optimal transport and sampling in the space of binary matrices with fixed margins to circumnavigate that step. So the full conditional of the cluster indicators looks like this. It's proportional to some very difficult number, but ZA belongs to this class of binary matrices so that the column and row sums are matched. So this is very difficult. I'll not get into the details of the clustering algorithm of the sampling algorithm, but as I mentioned, it first uses a discrete optimal transport, then uses non-uniform sampling task from the space of binary matrices with fixed margin. If you are interested to look more into this kind of sampling algorithms, you might want to check out this Miller and Harrison paper from 2013. I think it was published in Annals of Statistics, and a more recent paper by Guan Yang Wang from Rutgers, which was published in EJS, right? And we actually sort of play around with Wang's algorithm and build our own to sort of get rid of the problem. But if you're interested, I'll talk about the sampling algorithm later with you, but here I'm not presenting the details. Instead, I'm looking at a numerical example, right? So simply we have two clusters now. In the first class, suppose I have a protected attribute that has two levels. suppose I denote the labels by 1 and 2. In the first cluster, I generate 20 individuals belonging to A equal to 1, 30 individuals belonging to A equal to 2. And in the second cluster, I generate 30 individuals with A equal to 1 and 20 individuals with A equal to 2. So if you look at the totality of the cluster 1 and 2, you have 50 individuals belonging to A equal to 1, and you have 50 individuals belonging to A equal to 2. So in the entire sample, the ratio of 1 and 2 is 1:1. But in each of the clusters, the ratio is not maintained. So in the true data generating mechanism, we might not have the clustering constraints, the fairness constraints in place, right? And now we would try out various methods to see whether we could get clustering that has the balance constraint satisfied. So here I generate the cluster-specific models are normal. You could play around with it a bit and have models that are a bit misspecified. You can look at T or skew normal and so on and so forth. Multicolor case is the case where your protected attribute has more than 2 levels. And if you compare with the fair k-means, ours usually get higher fair score, which is the maximized cost that it can attain. So you have fixed the balance requirement. Given a balance requirement, what is the maximum fair score you can attain? You can think of it as the negative of the clustering objective. So higher is better. And across all the examples, you would see, as any other simulation example, we are better than everybody else. No surprises, right? And we try it out on a bunch of benchmark data sets. Again, we are better than the existing approaches. And since we have a model-based setup, we can choose the number of clusters in a data-driven manner, which is not true for k-means-based algorithms that are already there in the literature, right? Now, what we already have achieved, we have a model-based procedure that gives us a way to have uncertainty quantification. We can talk about optimal discovery, whether I have not talked about it, but once you have a model-based procedure, it's easy to talk about optimal discovery and clustering consistency. So we are good on that, but non-penetrative based, ultimately, it depends on certain modeling assumption, right? What sort of modeling assumption do you have in the component-specific densities and so on and so forth? So if there is misspecification, it could be challenging for us to determine the number of clusters that we have, what is the fair clustering configuration, and so on and so forth. So all the good things about model-based clustering, we could choose the number of clusters. We could have uncertainty quantification of the clustering indices. All those advantages would become a disadvantage when you have model misspecification, because none of those would be dependable, right? To that end, we develop a generalized Bayes algorithm, which can be looked at as a model-based algorithm, but a model-based procedure. At the same time, we would be a little more resilient in presence of model misspecification. So what is generalized Bayesian posterior? Yeah.
What if you have several protective factors? Not only one, which there are multiple steps, but several of them.
Yeah, actually, if you look at the fairness-based approach, they would have different approaches to go about this. But our model is written in such a manner, you could have any number of labels of the protected attribute and any number of sort of protected attributes as well. So you could have more than one protected attribute, and each of the protected attributes can have several classes. So what is generalized Bayesian posterior? So the first step is empirical risk minimization, right? You have some sort of data, U1, U2, UN, and you minimize some sort of objective so that you get your optimal theta, where theta is the parameter of interest. So your minimum and chi-square estimates, you could look at MLE like this, and most all empirical risk minimization tasks could be written as what we have in the first step. Now we could probably do a step that looks a bit stupid. We could just negate the loss and write it like this to get a likelihood and combine that with the prior pi theta and get a posterior. Now, the first time I saw it, I felt like this should be illegal, right? This should not be allowed. But thankfully, there are brilliant people in this BCD et al. Paper. They showed that this could be actually looked at as a rational update of beliefs. So this could be written, looked at as a posterior. So once you have done that, you can develop methods for choosing lambda, and that was sort of formalized in the following biometric paper in this by Holmes and Walker. So this could be looked at as valid posterior. Now what do? We have two loss functions, right? One loss function that we minimize to get the fairlets, and another loss function is based on getting the clustering once you've gotten the fairlets. So we define those loss functions to be L1 and L2. Your L2 could be any factorization loss, like the k-means loss. So remember how we would have gotten the fair clustering with fairlets? First getting the fairlets, the minimal sets that are fair, then you cluster the fairlet centers, right? So there are two loss functions involved. L1 is the loss function for fairlet decomposition, and L2 is the loss function for clustering. Your favorite loss function, k-means or k-median or something like that. Now, once you've done that, we could assume uniform priors on the space of clustering and the uniform prior on the space of all possible fairlet decomposition. Of course, you could do something else, but that's not the point of the paper. We wanted to keep the priors as simple as possible and non-informative. Then your posterior would look like this, and we can use the methods developed in this paper to sort of learn lambda 1 and lambda 2. And once you have learned lambda 1 and lambda 2, we could have gotten the posterior in a form where we could easily sample. How the sampling goes, the first step uses a similar discrete optimal transport based tricks and weighted rectangular loop trick, which is the second one is a sampling algorithm for binary matrices with fixed margins. And the second one is sampling the clustering indices. So given the fairlet decomposition clustering, finding the clustering indices, this could be done using M8 steps. In particular, we adapt a recent paper by Regan, Dunson, and Amy Herring in Biometrica that develops a generalized Bayesian clustering, but they do not have fairness constraints and so on and so forth, right? So second step is not so novel, but our contribution is sort of in sampling from the space of all possible fairlets. Same examples now pictorially. In the first example, I run the Regan et al. Paper that I talked about that does not have fairness constraints. And so this is when the generative model is multivariate normal. So there is no misspecification. And that this plot gives me the misclassification errors when there is no fairness constraint. And this row is our method. This is the map, and this is the misclassification error probability. If you look at around the edges, you see these two clusters, when there is no fairness constraint, we are only concerned about the clustering cost. And these clusters look well separated in some manner. But these clusters sort of borrow some points from within another cluster, right? Because we have these clustering, we have these fairness constraints. And consequently, if you look at the uncertainty configuration, you look at their boundary, there are very few points which are not blue, which are not very certain. But if you look at the uncertainty in our plot, there is much more. Because the stealing is a bit uncertain.
Let's say if you run your algorithm, this one seed, and then there's another seed, and there's another seed.
Yeah,
You'll
so,
get to-
so these plots are obtained. So you have a give sampling in place, you
Mhm.
run it up to a burn-in.
Mhm.
When you believe that you have convergence, you draw various samples.
And how do you choose the exact clustering afterwards?
Sorry?
Like, how do you choose the exact sample to use for clustering?
So this is the map one, the maximum a posteriori one.
Mm.
So the clustering configuration that maximizes the posterior.
Okay.
And this is computed from all possible samples. So if you could have gone through one of the existing algorithms, you'd get an answer like this,
Mhm.
but you'd not get uncertainty. This is our sort of the thing that we are getting more out of it. Now, if we have misspecification, each of your components are not normal, but T. And remember, we work with k-means objective, right? Which is like normal, not T. And if you look at the clustering, again, there is no stealing going on over there. Here is some stealing going on because of the fairness constraint, and misspecification is the added uncertainty due to the misspecification is shown in more sort of green and yellow and red points. Right? In the previous plot, mostly the uncertainty was 0. There was only few points where there was uncertainty, but in misspecified setup, you have a lot of uncertainty. So the USP of this methodology is you could, when there is misspecification, that could be sort of figured out looking at these plots, looking at the extent of uncertainty that you have, right? This is done for another benchmark data set, but there is nothing new. Again, when there is no fairness constraint, the clustering boundaries are well separated. But when there is fairness constraint, there is some sort of stealing going on. And due to the stealing, there is more uncertainty in the right-hand side as well. So this is existing algorithm that has fairness constraint, but no uncertainty quantification. This is our algorithm that has, we can get the map and uncertainty quantification for both. Right? So again, looking back, yeah.
So the jumbling up on it happens at the borders.
Yeah.
Right?
Because the game you play is a tug of war between clustering objectives and the balance constraints. So for maintaining the balance constraints, you have to steal. But where do you steal from? If you steal from the boundaries, the clustering objective is not that hampered. That's why the jumbling up happens along the border, right? So again, what we covered, existing literature, mostly optimization based, no uncertainty quantification. We have the notion of uncertainty quantification. We have a statistical framework. We could talk about optimal discovery, and we developed a model-based procedure, a non-parametric-based procedure to do that. We have a principled performance evaluation scheme, but that's not enough. Our like any model-based procedures, a non-parametric-based procedure can fall apart in presence of model misspecification. To that end, we develop a generalized Bayesian fair clustering, which can be interpreted as model-based, which is robust to model misspecification, and which gives us uncertainty quantification that we can rely upon. So these are the papers. First one is in archive, and second one is already in press. If you were interested, you could just scan it and get hold of it. That's it. Any more questions? Yeah.
So you said you're able to handle multiple protected attributes at one time?
Yeah.
Where
Why are you able to do that? Does that happen in the Fairlight construction or something, or the?
So you have to slightly change the model you posit. And so there is large literature on mixed membership and so on and so forth, where you could look at a bunch of individuals based on their membership to membership with respect to two different variables. Suppose I have these bunch of people, I could cluster you with respect to your habit of food and say choice of sport. Both of them could be done simultaneously using mixed membership models, and you could play the same game and adapt our setup to get to that.
Any more questions? All right, thank you again for your.
Thank you.